Hello, sir. Excuse me, sir.
Yeah, please.
So this is Anirban, sir. So did you receive all the the test
Yes,
responses from me?
I got it.
Thank you, sir.
Okay, so we have made a proxy submission. So we have the capability for, we have an option to submit on your behalf. We have made that. Okay, so I guess it is fine.
Sir, it's like, will this be problem? It's like in the next test as well. Will this prevail in the next test?
What was the problem actually?
So when I clicked on the submit button, it did not show anything to upload. Means did not show any option to upload.
It was
Even in
within
the
the
time
deadline.
limit. Yeah. Everything was within the deadline. I
Okay,
clicked the submit
we'll
button.
check out. We'll check
Hello,
out if there's.
Hello?
Yeah.
Actually, I was also facing the same problem. Like when select file, I was clicking, it wasn't showing any pop-up. So next time, maybe you can try drag and drop.
Oh, drag and drop. Okay, we'll also check if there is any bug from our side. Okay, hopefully it will be not be there, but see, be rest assured if you have done the test or assignment, you will not be penalized for failure of any of this. You can always mail me, we'll accept it within a time limit. So maybe within say 15 minutes of the end of the test, you mail me, we'll always accept it. That's not a problem.
Okay, thank you.
Wait,
so can you tell like approximately till when can we expect the result, like the marks?
Within 1 week. Within 1 week, you will get the marks. Okay, that is fine. Okay, so can you see the screen? Hello?
Yes, sir.
Yes,
sir.
sir.
Yeah, okay. So let me quickly complete one part that was pending in the last class. So it's binary to gray and gray to binary conversion. So let's look at this format. So the top bits, so we have 6-bit numbers. The top bits B5 to B0 are the binary bits, and the bottom one G5 to G0 are the gray bits. And these symbols, this plus, these are XOR. So addition modulo 2, these are XOR bits. So the rule is as follows. The most significant bit is identical for both binary and gray. So they are identical. And for the remaining, to find the ith binary bit, it is the it is the XOR of, you can check, it is the XOR of the I plus 1th binary bit and the ith gray bit. So 0 is 1 XOR. So ith binary bit is XOR of I plus 1th binary bit and the ith gray bit. Gi XOR bi plus 1 is bi. And similarly, you can write it as an equivalent rule. So the rule is as follows. So to find bi is you look at the number of preceding ones to bi. So if you in gi. So find bi. So you look at the number of I plus 1, I plus 2 up to the most significant bit, how many ones are there. If that number is if that number is even, then bi is a copy of gi. And if the number is odd, then bi is gi prime, is the complement of gi. Okay, so this is the rule. This can be actually shown to be equivalent to this thing. So this diagram, if you remember, it's fine. So G4, for example, is XOR of B5 and B4. G4 is XOR of B5 and B4. Okay, so this diagram, if you remember, it will be fine. Okay, anyway, let's move on to another topic. So far we have seen what is a different radix number system. We have seen different codes, which are basically representation of numbers. So each digit 0 to 9 is represented by some number of bits, maybe 4 bits in BCD. And these codes are kind of, they are convenient because they are easy to map numbers to binary representations. Binary representations because they are easy to handle in a computer. And these codes, we desired several properties. Properties, for example, they should be cyclic. That means the number of the having distance between codes of two successive numbers should be one. And similarly, we had a self-complementing code. That means if you take the 9's complement, it's nothing but the 2's complement of the code. No, sorry, not 2's complement, the flipping of the codes, flipping of the bits of the code. So we also said reflective code. That means if you reflect a code that means they are kind of extensible. So you take a m-bit code, you reflect it, append zeros and ones, you get a m+1 bit code. And all these properties, we can construct code in such a manner so that all these properties are satisfied. And these properties have some advantage. For example, in the cyclic code, the sensing error is a small error in the numbers is equivalent to a small Hamming distance in the codes. And other such properties are required. There are some more properties like they should be unique. That means no two code words. And single number should not have two different code words. So these are some of the properties we studied. There is two more important properties, which is kind of extension of these codes, this gray code, BCD code, or whatever, which is often desired. Even now they are often desired. There are two properties. One of the properties is known as error detection. So what happens is that when we read these bits in a computer, say in a CPU, many of these bits are loaded from the hard disks. And the hard disks, it's magnetic memory, so there are often error in the data. When you read from using a magnetic coil from the hard disk, sometimes there is an error. The 1 is read as 0 or 0 is read as 1. There are errors. Similarly, for example, there may be other types. When you're typing from the keyboard, there may be errors and that. So inside the computer, inside the CPU, there is in almost all the steps, there is a error detection and correction that is done. You might have heard that every disk has something called a CRC, cyclic redundancy check. That's basically a method of detecting errors. Okay. Also, similarly, let's say when you are communicating say over a network, say wireless network or a wired network, of course, always there is a error. What you transmit, the packets are lost or something, or there is some error. So what almost all the networking protocols do is that they have kind of error detection and error correction built in the connections. Okay, and so this is very important step. What we mean by error detection is if you have a bit string, whether this was the intended bit string or not, that we call as error detection. So that means there is we say that there is at least an error, say 1-bit error or k-bit error in the binary string that we have received or read or whatever. This is error detection, but we are not yet in a point. We just know there is error or not. We are not in what in doing error correction is first we detect whether there is error or not. Then also we find out in which bit position there is an error, or not just that overall string there is an error, in which particular bit position there is an error. And if we know in which particular bit position there is an error, we'll just flip that bit, because error means 0 can be 1 or 1 can be 0. We can just flip that bit and correct the error. So that is known as error correction. Let us start with error detection. So always, if you want to do error detection, or for that matter correction also, you have to have redundant bits in the codes. You have to have redundant. Without redundant bits, you cannot do error detection or error correction. So the scenario is like this. So you have a set of data bits or information bits, which is the actual numbers or values that you want to store. Along with that, you have some number of bits called redundant bits, which are not data bits, and they are called check bits or checksum bits. These are check bits. So these check bits may be either appended in the end of the data bits, or they may be interspaced in the inside the data bits. These check bits help you in error detection as well as correction. And these check bits are actually derived by some algorithm. They are derived from the data bit by some algorithm. So they are computed. So the data bit is either generated by a human or a hard disk or whatever source communicated. Once you receive the data bits, once you read the data bits, you compute the check bits by looking at the data bits. And these check bits you append to the data bits. And the data bits plus check bits together forms what is as a code word. So the code word is slightly longer than just the data bits, which is originally intended, as it includes the check bits also. Okay, so how do you do error detection using check bits? The idea is as follows: all possible code words. Now code words I mean data bits plus check bits. All possible code words are categorized into two types, either valid codes or invalid codes. So there is some property we define, and if we check that property of the code word, if that property is satisfied, we call it as a valid code. If that property is not satisfied, we call it as an invalid code. And they are designed in such a way that an occurrence of an error, if somehow there is an error, a valid code becomes an invalid code. A valid code is transformed into an moment there is an error, moment somehow an error occurs, a valid code no longer stays valid. It becomes an invalid code. Okay, so a valid code will convert into a. So basically what we can do is that we can just do this property checking on the code. And by after the property checking, we find out that if this is an invalid code, we are sure that there is an error. That means we detect an error. So the error detection is nothing but this property checking on the code word, so to check it is valid or not. Okay, now if we by virtue of this concept, this way of error detection, one thing becomes obvious about some property of the valid codes. So this is usually stated in terms of something called a Hamming distance. So I have already discussed in the previous class that Hamming distance between a pair of code words is nothing but the count, the number of bits in which these two code words differ. Number of bits in which these two code words differ. So let me try to write down. So if we take two code words, say W1 and W2, 0101, and this is 1100. So the Hamming distance between these two would be 2. DW1, W2 would be 2. Okay, so now one property becomes clear that if you take any two valid code word, their minimum distance. So this error, this may be either an 1-bit error, the simplest, or this can be an k-bit error. 1-bit error means only 1 bit has been flipped. K-bit error means at most k-bit has been flipped. So if you want to detect k-bit errors by this valid invalid codes, the distance between two valid codes should be greater than equal to k plus 1. Distance meaning Hamming distance. Distance between two valid k words has to be at least k plus 1. Why? There is a very intuitive way of looking at that. Say these are all your valid code words. These are all your valid code words. Okay, so imagine an error perturbing a valid code word by say some delta Hamming distance. Perturbs because of the error, the new code word that we get, the corrupted code word, is delta Hamming distance from the code word from which it was generated by error. Okay, so if this delta is kb, this delta is k bit, so two code words should be at least separated by k plus 1 bits. Otherwise, what will happen? This perturbed, so this we call W, this is W plus delta, and this should be at least W plus k plus 1 bits apart, having distance. Because otherwise, what will happen is that if delta is k bit, so the other code words, the nearest code words, if they are less than k plus 1 bits together, this W plus delta may as well be a valid code word. So our scheme fails. Our scheme of valid and invalid detection, that fails. So this is what we need, that if you want to detect k bits of error, the distance, the Hamming distance between two valid code words should be greater than equal to k plus 1. So in order to detect 1 bit error, you have to at least have a Hamming distance between two code words to be 2. You can actually show that if you want to correct k bit words, you will need, so if you want to correct, say for example, 1 bit error, you need at least three Hamming distance between two valid code words. Okay, so let's see why. So suppose this is like this. So this is yes. Let me write it here. So this is a valid code word 1, and after the error, it can go to any of these. It can go to any of these. Say after 1 bit error, it can get perturbed to any of these. Any type of error can be in any position, so it can get perturbed. And you have another valid code word, let's say call it W1. This also maybe by error gets perturbed to this by 1 bit error or something. Okay, it gets perturbed to it. But what we don't want in error correction, what we want in error detection is that after perturbation, this should not be a valid code word again. This should not be what we get after error perturbation should not be a valid code word. Then only the scheme of error detection will work. In error correction, what we want? So W1, let's say it gets perturbed to this. W2 gets perturbed to this. W1 gets perturbed to this, and these two should not be the same. Why? Then we don't know after, because we are observing this error corrupted thing. So we don't know this has resulted in from W1 or W2. So you cannot reconstruct it back. You cannot correct it back. Okay. So these two should, so two different valid code words after error should not get mapped to a identical new code word. Then we cannot do error correction. Then there's an ambiguity. You can either correct it to this or you can correct it to this. So that should not happen. In order for that to happen, what is required? It requires that these two are sufficiently distanced apart. How do I know these are sufficiently distanced apart? Because then the distance between these two has to be at least 3. At least 3. Because if there are 3, this may go to a 1 bit distance. So this may become, say, you can reduce 1 bit distance from this 3, it can become 2. And this again can become 1 less. So it can be, so still 1. So if this distance was only 2, this W1 may come to this 1 bit distance. This may go to this 1 bit distance. So 1 plus 1, 2. So 2 distance, this will not work. So this has to be at least 2. Sorry, this is 1 bit. So this has to be at least 2. Then you can unambiguously reconstruct back. Okay, so now the thing is, we'll talk about error correction later. First talk about error detection. So now error detection, we know 2 valid code words should be at least k plus 1 Hamming distance apart. How do you ensure that? The way to ensure that is by means of redundancy. You put in your redundant bits, the check bits, you control them in such a manner, you compute them in such a manner so that this property is established. Let's see one scheme. One of the most simplest or the earliest scheme is based on something called a parity of the code word. Okay, so a code word is said to be of even parity if the number of ones in the code word is even, and a code word is to be odd parity if the number of ones is odd. And we take a convention called an even parity convention. Even parity convention. What it means, we say that all valid code words should have an even parity. All valid code words should have an even parity. Okay, so what I am trying to say is that, so this green ellipse, this set of green set, it means only even parity code words are valid. If it is odd parity, then it is an invalid code. This is just a convention. You could have done the other way also. Okay, so our property check is nothing but we check the parity of a code word. If we find it to be even, we know there is no error. If we find it to be odd, we know there is an error. So that's the simple error detection. Okay, now naturally the question is, say data bits, they may be either even parity or odd parity. They can be anything. They can be either even parity or odd parity. So what you do, you set your check bits, in this case one single check bit for 1 bit error detection. You set your check bits to be in such a way that whatever be the parity of these data bits, even or odd, your check bits are controlled by means of this deterministic algorithm in such a way that the total code word always has even parity for a valid code. If it is odd parity, we will not consider it as a valid code. Okay, there is an error. So basically, you control the parity. You introduce your check bit is nothing but the parity bit. So if the data bits have odd parity, you just set your check bit to 1, so the total code word becomes even parity. And if your data bit is even parity, you set your check bit to be 0. Check bit in this situation will be called a parity bit to be 0, so that the total code word is also even parity. So the total code word check bit plus data bit has to be even parity. Okay, so the check bit just compensates for the odd parity in the data bit. So this scheme, this is an example. Look at the first set, the even parity BCD. This is an even parity BCD. You know, let's look at the numbers, digits from 0 to 9. You know that BCD is 4 digit, 8421 weight. So these first 4 columns are the BCD, normal BCD codes. The redundant 5th bit. So the data bits are these 8421. These bits are the data bits 0000 for 0 and so on. And you introduce a redundant 5th bit, the parity bit or the check bit, which it is set according to the convention I told before, that you see if the parity is even, 0 is considered to be even. If the parity is even, parity bit is 0. If the parity is odd, for example, say 1, the parity bit is 1. So that the total parity is always even. This is called an even parity convention. Even parity convention. Okay, so error detection is now very easy. You just look at the parity of the. So let's say in the receiver you transmit some data bit plus parity bit. The receiver end receives it. She computes the parity. If it is even, she accepts it as it is because there is no error. Now this parity should be all the total 5 bits, not only the data bits, should be for the total 5 bits. And if it is odd, definitely there is an error. So this is one possible scheme. Okay, there can be other schemes also. So there is something, this is an example. This is an example called a 2 out of 5. 2 out of 5. Okay, so 2 out of 5 means that you have a 5-bit code word which is redundant, because you know that to represent 0 to 9 you only need 4 bits, you don't need 5 bits. So still I am having 5 bits. I am having 5 bits with the convention that only 2, not less than 2, not more than 2, exactly 2 bits out of this 5 bits will be 1, rest will be all 0. Okay, exactly 2 out of these 5 bits will be 1, rest will be all 0. So this is correct, 2 out of 5 code. You can easily see that you can place, so you can place your 1 only in 2 position, if you can, of this 5 position. So 5 choose 2 is 10. So you can have 10 different code words, and each of these code words are mapped to one of the integers 0 to 9. One of the digits, decimal digits 0 to 9. They are mapped to them. Okay, so 5 choose 2 is 10. You can do that. So this is a 2 of 5 code. So how do you check error in this code? So moment any of the bits get flipped, it is no longer 2 of 5. It's no longer 2 of 5. Okay, there will be either less number of 2s or more number, less number of 1s or more number of 1s. So this is no longer 2 of 5, 2 out of 5 code. Okay, so in fact this is a you can generalize it to say m of n codes. You can choose both m and n according to your wish, depending on how many different entities you want to represent. Okay, m and n code. And in fact, this was actually first suggested by Donald Knuth, a very famous computer scientist. I guess all of you have heard the name, Donald Knuth. So these are actually called constant weight codes. Constant weight codes. Okay, the idea is that Hamming weight of code word W is nothing but the Hamming distance between W and an all zero code word of the same length as W, of an all zero code word. So which basically means the number of ones in W. Which basically means the number of ones in W. So this is called the Hamming weight of a code. And you see in 2 out of 5 code, all the code words have the same Hamming weight too. Similarly, in M of n code, all the code words will have an Hamming weight of n. So these are called constant weight codes. There is the early computers, some IBM 754, the earliest computer. In fact, Hamming was an mathematician. He worked in the Los Alamos nuclear bomb project, the Manhattan project. And Hamming was of the earliest people who designed a computer. So in the Los Alamos project, people who had used IBM mechanical calculators, the electronic calculators. So they used to calculate a lot of things. And even in such systems, there were errors from reading the punch cards, if you have seen them. So they're reading the punch cards. So Hamming was an engineer there. He suggested this idea of Hamming distance coding and all these things. So constant weight codes are kind of a little more sophisticated than even parity codes. They have a constant weight, but the problem is that in this case is fine, but finding a general M of n code, satisfying the Hamming separability criteria, it's pretty non-trivial. So there are complex algebraic systems like Steiner systems and such partitioning systems which are used to construct more complicated M of n codes. So it's an algorithmic problem actually. It's a hard problem to construct M of n codes. Okay, but so 2 of 5 code early computers, there are ways now, but there is one place that it is still used. All of you, here is an example. You see, this is an example of a barcode. You see in any product you buy in any shop, you will have this barcode. So they have this optical scanner, they read this. So these barcodes, the coding is like this. You can see there are vertical white and black strips. A thicker strip is represented by an 1, and a narrow strip, normal narrow strip, is represented by an 0. Sorry. Yeah, the wider strip is 1, the narrow strip is 0. The black strips are considered. And you see there are this 0 to 9, these are there. And there are groups of 5 such vertical bars that are kept. And then read this bar, if you can see it, if you group into, I'm leaving it as an exercise, if you group into groups of 5, you will see exactly 2 bars are thick, not more than them are thick. So it's a 2 of 5 codes. There are 5 bars per digit, per number, and they are exactly 2 are thick. And of course, in barcode, you need a lot of error detection. If it is not properly read, you might have seen that if they sometimes they put the optical reader, if it is not proper, they again place it, again try to read it. So they do an error detection. Only if there is no error, then they read it. The machine reads it. Okay, so these are examples. There is another weighted code. See, this is a 63210. So these are the 5-digit code, weighted BCD kind of code, but instead of 4 5 bits, which is also error detecting. You can easily find. One property you see of this all these 3 codes is that the Hamming distance. So all these are meant for 1-bit error detection. The Hamming distance between any 2 pair of the code words you see is at least 2. It's more than equal to 2 between any 2 codes. So in all these 3 codes. Okay, so that's an absolute. If it is not that, then it cannot act as. We have already explained it cannot act as error detection code. Okay, so in general, there are. This is a big subject. So there are a lot of research. There are books, journals, everything dedicated to just constructing code. For example, one of the things that you use in a hard disk is that, see here, for every different code word, I have a parity bit. Okay, so in a hard disk, what happens is that you know that hard disk is divided into blocks. There are this kind of rings, and then there are blocks in them. And you know, in a hard disk, only the entire block of bits. A block is say 512 KB of 512 kilobytes. So many memory is there in a hard disk. So what is done? The entire block is read at a time. You cannot read finer than that. You have to read the entire block and store it in the memory or whatever. So there is a parity bit. These are sometimes called block parity bits. So that means you look at the first 4 columns in any of this code, you chunk them into blocks, and you don't have parity bits for every word in every individual word in the block, but for entire chunk of this words block, you have a kind of shared parity bits. These are something called block parity bits. So that's more convenient, because anyway you are reading the entire chunk. So to reduce your parity check time, because see, parity check is an overhead also. You need some time to check the parity. So to reduce your parity check time, you do it 1 block at a time. So they are block parity codes. So CRC and all this, they are based on these block parity codes. Okay, so there are even much more sophisticated techniques. We have just touched the very basic things, which are the earliest things to do. Okay, so with this, I think I'll.
Hello.
Yeah, please.
So you said that the Hamming distance should be for 1-bit detection. The Hamming distance should be greater than 3, right? Means like if the if
for
W1,
error correction 3. For error detection, it should be greater than equal to 2.
Oh, okay.
So the idea is simple. See, the idea is, so this is a code word. This is a code word. So 1-bit error will move it to another code word. What I don't want is that this should not move to this. 1 bit should not convert one valid code to another valid code. It should convert it to an invalid code. It should convert to an invalid code. And what since this is 1-bit error, this another valid code should be at least 2-bit apart, greater than 2-bit apart, greater than equal to 2-bit apart. So that means 1-bit error will not count. So similarly, if you have k-bit error, this should be at least k plus 1 bit apart. And what we do in error correction is that we not only look at valid code. So these are 2 valid code words. One error will move here to here. Another error will move here to here. What we don't want is that both these 2 move to the same place. Then if you are correcting it back, you don't know where it has come from. So you don't know you want to correct it to this, or you want to correct it to this. So if these are 1 bit, then this distance should be at least greater than equal to 3 bits. Otherwise, this will not happen. Okay, so this is the idea. So now let us move to our error correction approach. So Professor CRM will look into this. Okay, so CRM. What happened?
I'll take over now. All right, so
CRM, I think you have to share your screen.
yeah, it is loading. Yeah. Okay. All right, so let us. Okay, so we'll let us look at a particular error correction code. So we saw that it is possible by with the addition of redundant bits, it is possible to both detect and correct errors. So of course intuitively you can expect that you will need more bits if you want error correction than just error detection. So first of all, let us just study one particular scheme for error correction. So let us say that you have got four data bytes, which are indicated here as D1, D1, D2. So these are your bytes. Let us say this is D1. My God. D2, D3, and D4. These are your four data bits. Okay, these are your four data bits. Of course, I mean, let us say that you got this four data bits. Now to these data bits, you want to add some extra bits to achieve error correction. So the extra bits are parity bits defined on subsets of these four bits. So let us say P1 is defined on D1, D2 and D4, all right, and P2 is defined on D1, D3 and D4, and so and P3 is defined on D2, D3 and D4. So as you can see, these parity bits are defined on three different subsets. So you can have three combinations of four items taken three at a time. Okay, so these are the these are the three subsets which are indicated, which are taken. All right. So if we now look at the effect of this, so suppose. So let us see what happens. So what is happening is that the situation is something like this. You have a transmitter here. You have a transmitter here, and you have a receiver here. All right, and you are sending these, or you can say these 7 items of data. This is one way of saying. So this is equal to 4 plus 3. 4 data plus 3 parity. So now we assume that only one bit, at most one bit will be in error. This is an assumption, okay? If this assumption is violated, this scheme will not work. So we assume that, so what happens is when you're transmitting data due to some noise, one of the bits might get flipped, all right? One of the bits might get flipped. So we assume that only one of the bits will be in error, any one of the bits. So let us see the effect of this bits going into error. So suppose D1 goes into error, then you can very easily see that parity bits P1 and P2 will be affected, whereas parity bit 3 will remain unaffected, all right? That is, so you can then check the effects of the other bits also. So you can see that if D2 goes into error, then P1 and P3 will be affected, whereas P2 will remain unaffected. So that way you can see that if D3 goes into error, only P2 and P3 are affected, whereas P1 remains unaffected, all right? And if D4 goes into error, then all of these are affected, all right? So what you find is that if there is an error in the data, at least 2 parity bits will be affected, all right? At least 2 parity bits will be affected. So what are you going to do? What is the basic scheme? The basic scheme is if we go back here, so you are going to transmit, right? So you compute the parity bits here. So here you have D and P, all right? You have got D and P. Basically, you have computed these parity bits from this data, and over here, what you have is D dash and P dash. All right. So over here, the assumption is at most one bit is in error. So you are going to compute the parities once again. Okay. So here you are going to compute the parities once again. Here also, here you have computed. So this is, and you are going to, all right, not P dash, but rather P dash dash. So you're recomputing the parities from these data bits, and then you are going to compare. You compare P dash to P dash dash, because P dash is what you have received and P dash dash is what you are computing. So you do not initially, there could be a single bit error anywhere in D or in P. So according to the the analysis that you have done, you know which of these will be affected. So what you see is that if any one of these data bits are in error, at least 2 parity bits will be affected. If D4 is in error, all the 3 parity bits will be affected. And if D1, D2 or D3 are in error, then exactly 2 of the parity bits will be affected, as you can see. Now, of course, the parity bits could also be in error. So if parity bits are in error, then what you find is that nothing else is affected. So suppose P1 is in error. So that is the only thing that will be affected. Nothing else will be affected. So if the parity bits are in error, then nothing else will be affected. So based on this understanding of how these bits get affected, you can then have a decision mechanism to determine exactly which bit. So you are not only understanding that there is an error, but you are able to pinpoint the bit which is in error. So you can actually pinpoint. So you are more interested in the data bits, of course. So in particular, if the data bits are in error, I mean you can correct any one error, but of course you don't gain much by correcting the parities. But this scheme allows you to correct any single bit error, either in the data or in the parity. Okay, as you can see. But we are interested in recovering the data correctly. So parity is only to help us to recover the data correctly. All right. So that way we can we can have a scheme. You can design the logic. So what we do is we number the bits in this manner. So let us say, so as you can see, we have got 7 bits here, right? 4 bits of data and 3 bits of parity. So we can number the bits from 1 to 7, and if we number the bits from 1 to 7, we can say that bit 1 is is P1, bit 2 is P2, bit 3 is no, bit 2 is P2, bit 3 is D1, bit 4 is P3. So suppose this is how we index the bits, okay, as shown in the table, and the association which are shown in the diagram and over here also, that same association is presented here in tabular form, okay, the same association. So as you can see, the D4 affects all the 3 parity bits, D3 affects only P3 and P2. So these data bits, as you can see, are affecting only 2 parity bits, and D4 is affecting all the 3 parity bits, and the parity bits are affecting only themselves. So this parity bits, if these are in error, they only affect themselves. So so what you can see, that bits at 2 to the power I positions, that is 1, 2 and 4, are for parity, and the others are for data. So yeah, so P1 covers data bit positions having 1 in the LSB. All right. So yeah, so as you can see, P1 covers data bit positions having 1 in the LSB. So that is 1, 3. So you can see those are colored here for your convenience. You can see that this magenta P1. So wherever you have P1, you find that you have 1 in the least significant bit position of the bit encoding. All right. So similarly, you have this P2 covers data bit position having 1 in the next bit position. So what happens is that this allows you to construct the logic bit optimally. Okay. So this kind of indexing helps you to construct the logic optimally. All right. So we will take up the exercise. We'll take up the exercise of constructing the logic for error recovery using this scheme. Okay, you can construct the logic for error recovery using this scheme. This we will discuss. I mean, we'll give this as a lab experiment, and we can discuss it. Discuss the experiment on Monday. So we'll see how that can be done. You can also take that as an exercise. All right, and now let us just talk a bit about error error correcting codes. So look at this cube, okay, look at this cube, and let us say that we are considering two particular codes, okay, all zeros and all ones, okay. We are considering two particular codes, all zeros and all ones, that is this one, all zeros and all ones. All right. Now, suppose you can a single bit error is allowed. I mean, let us say that any one bit can go into error. I mean, we are assuming that only a single bit. So these are the possible erroneous bits. Okay, so 000 can become 100, 001, or 010. Okay, these are the possible error bits. These are the possible, error codes that you can have from this all zero going into error. Okay, and similarly, if any one of these bits go into error, then these are the possible error codes. And the nice thing that you see is that these are separated. Okay, these codes are separated. So if you have any of these codes, you can trace it back to this, right? You can trace it back to this. You know that these codes must have come from, these error codes must have come from this. And similarly, you can trace it back to this. I mean, this is what you are saying is this is possible because these codes are different. Okay, these codes do not map. So what you see is that the distance. Okay, what is the distance? If you look at the distance, this is the the distance. The Hamming distance is this is 1, this is 1, and this is 1. So the Hamming distance is 3. Okay, this is the Hamming distance of 3. This is the Hamming distance that you must have between any two valid code words. Okay, Hamming distance of 3 is required between any two valid code words to ensure that you can trace the error back to the valid code. Okay, so there is no intersection of of the erroneous codes. The erroneous codes remain disjoint. So it is possible you don't lose information. Okay, you don't lose information. You have adequate information to go back to the original code. Okay, so this is what you see, and you can see that if d is the minimum Hamming distance between code words, then up to d minus 1 by 2, the floor of that bits can be bit errors can be corrected. Okay, so this allows you to determine how much of error correction you can have. So let us look at a little bit of arithmetic based on this principle. I think we'll take it up in the next class because this class
I think time is over. Huh?
Yeah, so we'll do the rest in the next class. All right, okay, thank you then. Yeah.
So on Monday's lab, we'll do the code.
Yeah, Monday we'll cover the rest of the theory and maybe something else, and we'll also take up this how you can design. We'll take up the design of single bit error correction. All right, we'll stop here now. Yeah.